Welcome to Loops and Loops, your gateway to the fascinating world of chemistry. Chemistry, often called the central science, underpins the very fabric of the universe, from the composition of atoms to the complexity of molecular interactions. Join us as we embark on an enlightening journey through the realm of chemistry, exploring the building blocks of matter, unraveling the mysteries of chemical reactions, and discovering the profound impact of chemistry on our everyday lives. Whether you're a chemistry enthusiast, a curious learner, or simply intrigued by the wonders of the molecular world, you're in for an immersive experience. So tighten your loops, prepare to dive into the periodic table, and let's explore the captivating world of chemistry together. Chemistry is the scientific discipline that explores the properties, composition, structure, and behavior of matter at the atomic and molecular levels. It is often referred to as the central science because it bridges the gap between physics, biology, and other natural sciences. At its core, chemistry seeks to understand the fundamental principles governing the interactions and transformations of matter, from the smallest particles to the vast complexities of the universe, through experimentation, observation, and theoretical modelling. Chemists uncover the mechanisms behind chemical reactions, the formation of new substances, and the energy changes associated with these processes. One of the key concepts in chemistry is the idea that matter is composed of atoms, which are the building blocks of all substances. Atoms combine to form molecules through chemical bonds, and these molecules can undergo various types of reactions, including synthesis, decomposition, and exchange reactions. Chemists study the structure of molecules and the forces that hold them together, such as covalent bonds, ionic bonds, and hydrogen bonds, to predict their properties and behavior in different environments. Chemistry encompasses a wide range of subdisciplines, including organic chemistry, inorganic chemistry, physical chemistry, analytical chemistry, and biochemistry, each focusing on different aspects of matter and its interactions. Organic chemistry, for example, examines the structure, properties, and reactions of carbon-based compounds, which are central to life processes and the synthesis of pharmaceuticals, polymers, and materials. Inorganic chemistry, on the other hand, investigates the properties and behavior of non-carbon-based compounds, including metals, minerals, and semiconductors. Physical chemistry explores the principles governing the behavior of matter and energy at the atomic and molecular levels, providing insights into phenomena such as chemical kinetics, thermodynamics, and quantum mechanics. Analytical chemistry focuses on the development and application of methods for detecting, identifying, and quantifying substances in samples, ranging from environmental pollutants to pharmaceutical drugs. Biochemistry delves into the chemical processes occurring within living organisms, including metabolism, enzyme kinetics, and molecular genetics, elucidating the molecular basis of life and disease. Chemistry is a diverse and multifaceted science that plays a central role in understanding the natural world and addressing global challenges in areas such as energy, healthcare, materials science, and environmental sustainability. By uncovering the underlying principles governing matter and its transformations, chemists continue to push the boundaries of scientific knowledge and innovation, driving progress and advancements in countless fields. The history of chemistry is a captivating narrative that spans millennia, tracing the evolution of humanity's understanding and manipulation of matter. Ancient civilizations laid the foundation for chemical knowledge through practices such as metallurgy, dyeing, and medicine. In Egypt, for example, artisans mastered the art of alloying metals, while Chinese alchemists experimented with herbal remedies and chemical processes. These early endeavors, rooted in practical applications, laid the groundwork for the emergence of alchemy, an esoteric pursuit that sought to transmute base metals into gold and discover the elixir of immortality. As civilization progressed, so too did the study of chemistry. The ancient Greeks, with their philosophical inquiries into the nature of matter, proposed fundamental ideas that would shape the course of scientific thought. Democritus introduced the concept of atoms as indivisible particles that make up all matter, while Aristotle's theory of the four elements and the principles of matter and form provided a framework for understanding the physical world. These early philosophical musings laid the groundwork for more systematic investigations into the nature of matter in the centuries to come. During the Islamic Golden Age, scholars in the Islamic world made significant contributions to alchemy and chemistry. Some figures pioneered experimental techniques, developed laboratory apparatus, and made advancements in distillation, sublimation, and crystallization. Their meticulous observations and experimental methods paved a way for the scientific revolution in Europe, where alchemy gradually gave way to modern chemistry. The scientific revolution of the 17th and 18th centuries ushered in a new era of scientific inquiry and discovery. Figures like Robert Boyle, known as the father of modern chemistry, conducted groundbreaking experiments on the properties of gases and the nature of elements. Antoine Lavoisier, through his meticulous measurements and rigorous experiments, established the law of conservation of mass, identified oxygen as a key component of combustion, and introduced systematic nomenclature and experimental techniques that laid the foundation for modern chemistry. In the 19th and 20th centuries, chemistry experienced rapid expansion and specialization. The discovery of new elements, the development of organic chemistry, physical chemistry, and biochemistry, and the Industrial Revolution propelled chemistry into new frontiers of exploration and application. Imagine that atoms are like tiny, invisible Lego bricks. They're the smallest units of matter, and they come in different types, each with its own unique properties. We have atoms like hydrogen, oxygen, carbon, and many others, and they all have different shapes and sizes. Now, when atoms come together, they form molecules. Think of molecules as Lego structures built from different types of bricks. For example, when two hydrogen atoms join with one oxygen atom, they create a molecule of water, just like when you stack Lego bricks together to build a house. But atoms and molecules are always moving and interacting with each other. And that's where chemical reactions come into play. Chemical reactions are like Lego transformations. They change the arrangement of atoms and molecules to create new substances. For instance, when you mix baking soda with vinegar, you get a chemical reaction that produces bubbles of carbon dioxide gas, just like when you mix different coloured Lego bricks to create a new design. Now let's talk about the different types of substances we encounter in chemistry. We have elements which are like the basic colours of Lego bricks. They can't be broken down into simpler substances. Then we have compounds, which are like complex Lego structures made from different types of bricks. Finally, we have mixtures, which are like Lego sets with different types of bricks all mixed together. Chemistry is all about understanding the properties of matter, and how atoms and molecules interact, and how we can use that knowledge to create new substances and solve real-world problems. Elements are the building blocks of matter, and each element is made up of atoms with the same number of protons in their nucleus. They are arranged in the periodic table, a chart that organizes elements based on their atomic number, which represents the number of protons in the nucleus of an atom. The atomic number of an element is the number of protons in the nucleus of an atom of that element. It determines the identity of the element and its unique properties. The atomic mass of an element is the average mass of all isotopes of that element, taking into account their relative abundance. It is measured in atomic mass units. Elements are represented in chemical equations using symbols derived from their names. For example, oxygen is represented by the symbol O, and hydrogen is represented by the symbol H. Compounds are substances composed of two or more different elements chemically bonded together in fixed proportions. They have unique properties distinct from those of their constituent elements. Compounds are formed through chemical reactions, where atoms of different elements combine to form new chemical bonds and create new substances. Chemical bonds are forces that hold atoms together in compounds. The main types of chemical bonds are ionic bonds, covalent bonds, and metallic bonds. Ionic bonds form between ions, which are charged atoms or molecules. They occur when electrons are transferred from one atom to another, resulting in the attraction between positively and negatively charged ions. Covalent bonds form when atoms share electrons to achieve a stable electron configuration. They occur between non-metal atoms and can be either polar or nonpolar, depending on the electronegativity difference between the atoms. Chemical formulas for compounds indicate the types and numbers of atoms present. In a compound, they use element symbols and numerical subscripts to represent the composition of the compound. Stoichiometry is the branch of chemistry that deals with the quantitative relationships between reactants and products in chemical reactions. Stoichiometry is used to calculate the amounts of reactants needed and products formed in chemical reactions based on the principles of conservation of mass and energy. The law of conservation of mass states that mass is neither created nor destroyed in a chemical reaction, meaning the total mass of the reactants equals the total mass of the products. The law of conservation of energy states that energy cannot be created or destroyed in a chemical reaction, although it may change forms. The molar mass of a compound is the mass of 1 mole of that compound and is expressed in grams per mole. The molar mass of a compound is calculated by summing the atomic masses of all the atoms present in the compound, taking into account their respective molar ratios as indicated by the chemical formula. The mole concept in chemistry is a way of counting and comparing amounts of substances. It's like a counting unit, just as you would use a dozen to represent 12 things. In chemistry, a mole represents a specific number of particles, whether they are atoms, molecules, or ions. Empirical formulas are determined from experimental data, often from elemental analysis or mass spectrometry. By comparing the masses of the elements in a compound, you can find the simplest ratio of atoms present. Chemical equilibrium occurs when the rates of the forward and reverse reactions in a chemical system are equal. This means the concentrations of reactants and products remain constant over time, although they may not be equal. Chemical equilibrium is achieved through the dynamic interplay of forward and reverse reactions. When the rates of the two reactions become equal, the system reaches equilibrium. The equilibrium constant is a numerical value that expresses the ratio of product concentrations to reactant concentrations at equilibrium for a chemical reaction. It's a measure of the extent to which a reaction proceeds to form products. The equilibrium constant is calculated by taking the concentrations of the products raised to their stoichiometric coefficients and dividing by the concentrations of the reactants raised to their respective coefficients. Reversible reactions can proceed in both the forward and reverse directions, while irreversible reactions proceed only in one direction. Le Chatelier's principle states that if a system at equilibrium is subjected to a change, it will adjust to counteract that change and restore equilibrium. For example, if you increase the concentration of a reactant, the equilibrium will shift to favour the formation of products. Factors that affect a position of equilibrium include changes in concentration, pressure, temperature, and the presence of catalysts. Homogeneous equilibrium occurs when all the reactants and products are in the same phase, while heterogeneous equilibrium involves reactants and products in different phases. Equilibrium expressions are written using the concentrations of the substances involved in the reaction, with each concentration raised to its stoichiometric coefficient. For heterogeneous reactions, concentrations of solids and liquids are typically omitted from the expression. Acid-base chemistry deals with the behaviour of acids and bases in chemical reactions. Acids are substances that donate protons, while bases are substances that accept protons. They play crucial roles in various chemical processes and biological systems. The Arrhenius definition defines acids as substances that increase the concentration of hydrogen ions in aqueous solutions, and bases as substances that increase the concentration of hydroxide ions in aqueous solutions. However, the Arrhenius definition is limited to aqueous solutions. The Bronsted-Lowry definition expands the concept to include reactions that occur in non-aqueous solvents. According to this definition, acids are proton donors and bases are proton acceptors. The Lewis definition is even broader, defining acids as electron pair acceptors and bases as electron pair donors. This definition allows for the classification of substances beyond the traditional proton transfer reactions. The pH scale ranges from 0 to 14, with pH values below 7 indicating acidic solutions, pH 7 indicating neutral solutions, and pH values above 7 indicating basic solutions. The pH scale is logarithmic, meaning that each whole number change in pH represents a tenfold change in hydrogen ion concentration. So a solution with a pH of 3 has 10 times the hydrogen ion concentration of a solution with a pH of 4. The dissociation constant for acids and for bases are measures of their strength. Ka is the equilibrium constant for the dissociation of an acid, while Kb is the equilibrium constant for the dissociation of a base. Buffers are solutions that resist changes in pH when small amounts of acid or base are added. They are typically composed of a weak acid and its conjugate base, or a weak base and its conjugate acid. Buffers resist changes in pH by undergoing reversible reactions that either consume or produce hydrogen ions, depending on whether an acid or base is added to the solution. Titration is a technique used to determine the concentration of an unknown solution by reacting it with a solution of known concentration of another substance. In titration, an indicator is a substance that changes colour when the reaction between the titrant and analyte is complete. This colour change signals the endpoint of the titration. Indicators change colour during titration because they exist in different forms depending on the pH of the solution. The colour change is due to the different absorption spectra of these forms. Oxidation reduction chemistry involves reactions in which electrons are transferred between reactants. Oxidation is the loss of electrons, while reduction is the gain of electrons. Redox reactions always occur in pairs, where one substance is oxidized and another is reduced. Oxidation numbers are assigned to atoms in compounds, or ions to indicate the number of electrons that an atom has gained or lost compared to its elemental form. The oxidation number reflects the charge the atom would have if the shared electrons were assigned to the more electronegative atom in the bond. A half reaction in redox chemistry represents either the oxidation or reduction part of a redox reaction. It shows the transfer of electrons between reactants and products, allowing us to track the electron flow in the overall reaction. Oxidizing agents are substances that gain electrons and undergo reduction, causing another substance to lose electrons and undergo oxidation. Reducing agents are substances that lose electrons and undergo oxidation, causing another substance to gain electrons and undergo reduction. The activity series is a list of metals arranged in order of their reactivity. It can be used to predict whether a given redox reaction will occur. A metal higher in the activity series can displace ions of a metal lower in the series from their compounds in solution. Electrochemistry is the branch of chemistry that deals with the relationship between electricity and chemical reactions. It involves the study of how chemical reactions cause the flow of electric current and how the flow of electric current can cause chemical reactions. An electrochemical cell is a device that converts chemical energy into electrical energy or vice versa. It consists of two electrodes immersed in an electrolyte solution. During the redox reaction, electrons flow from the anode to the cathode through an external circuit. Electrons are transferred in an electrochemical cell from the species being oxidized to the species being reduced through the external circuit. This flow of electrons creates an electric current. Galvanic cells produce electrical energy from spontaneous redox reactions, while electrolytic cells use electrical energy to drive non-spontaneous redox reactions. Cell potential, or voltage, is a measure of the tendency of a redox reaction to occur spontaneously. It is calculated by taking the difference in standard electrode potentials between the cathode and the anode. The Nernst equation relates the cell potential of an electrochemical cell to the concentration of reactants and products involved in the cell reaction. It provides a way to calculate the cell potential under non-standard conditions. Electrolytes are substances that conduct electricity when dissolved in water or melted. They dissociate into ions, allowing the flow of electric current. Faraday's law of electrolysis states that the amount of a substance produced or consumed during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte solution. Coordination compounds are complex molecules composed of a central metal ion or atom bonded to surrounding molecules or ions called ligands. These ligands coordinate to the central metal through electron pairs, forming coordination bonds. Coordination compounds are formed through coordination bonding, where the electron pairs from the ligands overlap with vacant orbitals on the central metal ion, creating strong bonds. In coordination chemistry, a ligand is a molecule or ion that binds to a central metal ion or atom to form a coordination complex. Ligands typically donate electron pairs to the central metal, forming coordination bonds. A complex ion is a charged species consisting of central metal ion bonded to surrounding ligands. These complex ions can be positively or negatively charged, depending on the charge of the central metal ion and the ligands. Coordination compounds exhibit isomerism, where molecules with the same chemical formula have different arrangements of atoms or groups in space. This can include structural isomers, where the atoms are bonded in different orders, and geometric isomers, where the spatial arrangement of ligands around the central metal differs. Nuclear chemistry is the branch of chemistry that deals with the study of nuclear processes, including radioactive decay nuclear reactions and the properties of atomic nuclei. Isotopes are variants of a chemical element that have the same number of protons, but different numbers of neutrons in their nuclei, resulting in different atomic masses. Isotopes of an element are identified based on their atomic mass, which is determined by the sum of the number of protons and neutrons in the nucleus. Radioactive decay is the process by which unstable atomic nuclei lose energy by emitting radiation. This process results in the transformation of one element into another. The different types of radioactive decay include alpha decay, beta decay, gamma decay, and electron capture. These processes involve the emission of alpha particles, beta particles, gamma rays, or capturing of an electron by the nucleus. Half-life is the time it takes for half of the radioactive nuclei in a sample to decay. It is used to measure the rate of radioactive decay and determine the stability of isotopes. Nuclear fission is a nuclear reaction in which the nucleus of an atom splits into two or more smaller nuclei, along with the release of a large amount of energy. Nuclear fission is initiated by bombarding a heavy nucleus with a neutron, causing it to become unstable and split into smaller nuclei, releasing additional neutrons and energy. The products of nuclear fission include two or more smaller nuclei, along with additional neutrons and energy. These neutrons can initiate further fission reactions in a chain reaction, leading to a release of more energy. Nuclear fusion is a process where two light atomic nuclei combine to form a heavier nucleus, releasing a large amount of energy in the process. Nuclear fusion differs from nuclear fission in that fusion involves the combining of atomic nuclei to form a heavier nucleus, whereas fission involves the splitting of a heavy nucleus into lighter nuclei. Challenges in achieving nuclear fusion as a viable energy source include the extremely high temperatures and pressures required to initiate and sustain the fusion reaction, as well as the containment of the plasma involved. Chemistry plays a crucial role in environmental science by providing insights into the composition, behaviour, and interactions of chemicals in the environment. Pollutants such as chemicals, heavy metals, and particulate matter can negatively affect air, water, and soil quality, leading to environmental degradation and harm to living organisms. Chemistry contributes to the study of climate change by providing knowledge about the composition and behaviour of greenhouse gases, as well as their sources and impacts on the climate system. The ozone layer is a region of the Earth's stratosphere that contains a high concentration of ozone molecules. Human activities, such as the release of chlorofluorocarbons, can deplete the ozone layer, leading to increased UV radiation reaching the Earth's surface. Chemical reactions in the atmosphere, such as the formation of ozone and the oxidation of pollutants, can influence air quality and contribute to the formation of smog and other pollutants. Acid rain is caused by emissions of sulfur dioxide and nitrogen oxides, which react with water vapor in the atmosphere to form sulfuric acid and nitric acid. Acid rain can damage soil, water bodies, vegetation, and infrastructure. The chemistry informs the study of water quality and pollution by providing methods for analysing water samples, identifying pollutants, and developing strategies for remediation and conservation. Major sources of water pollution include industrial discharges, agricultural runoff, sewage, and littering. These pollutants can contaminate water sources and threaten aquatic ecosystems and human health. Contaminants can be removed from water through various chemical processes, such as coagulation, flocculation, sedimentation, filtration, and disinfection. Biomimicry is the practice of emulating nature's designs and processes to solve human problems. Chemistry plays a role in biomimicry by providing insights into the chemical properties and interactions of natural materials and processes. Chemical principles are applied in pharmaceuticals and drug development to understand the structure and function of molecules, design new compounds, and optimize drug formulations for effectiveness and safety. Chemistry plays a crucial role in agriculture and food production by providing insights into the chemical composition of soils, fertilizers, and crops, as well as the development of pesticides to protect crops from pests and diseases. Pesticides and fertilizers are developed through chemical synthesis and are used in agriculture to control pests, weeds, and diseases, as well as to provide essential nutrients to crops for optimal growth and yield. Food chemistry involves the study of the chemical composition, structure, and properties of food, as well as the interactions between food components during processing, storage, and consumption. It plays a critical role in ensuring food quality, safety, and nutritional value. Synthetic materials are human-made materials produced using chemical processes. These materials include plastics, polymers, ceramics, and composites, and they are used in a wide range of applications, from manufacturing and construction to electronics and healthcare. Chemistry contributes to the development of new materials by providing methods for synthesizing and characterizing materials with specific properties, such as strength, conductivity, and biocompatibility. Nanotechnology is the study and manipulation of matter at the nanoscale, where materials have unique properties compared to their macroscopic counterparts. Chemistry intersects with nanotechnology through the synthesis and characterization of nanoparticles, which are used in various applications, including medicine, electronics, and environmental remediation. Nanoparticles are synthesized using chemical methods such as precipitation, Sol-Gel synthesis, and chemical vapor deposition. They are utilized in diverse applications such as drug delivery, catalysis, imaging, and sensing. The use of nanotechnology in chemistry raises ethical considerations regarding potential risks to human health and the environment, as well as issues related to privacy, security, and societal impacts. It is essential to consider these ethical implications when developing and deploying nanotechnology-based products and technologies. Chemistry plays a vital role in forensic science, and criminal investigations by providing methods for analysing physical evidence such as fingerprints, bloodstains, and fibres to link suspects to crime scenes and establish guilt or innocence. Chemical analyses such as chromatography, spectroscopy, and mass spectrometry are used to gather evidence in forensic cases by identifying and quantifying trace substances, determining their origin or source, and reconstructing events based on chemical signatures. Chemistry contributes to art conservation and restoration by providing methods for analysing and preserving artworks and artefacts. Chemical processes such as cleaning, stabilisation, and conservation treatments are used to protect cultural heritage objects from deterioration and damage over time. The chemistry of cosmetics and personal care products involves the formulation, production, and testing of products for skincare, hair care, hygiene, and cosmetics. Chemical properties such as stability, safety, and efficacy are essential considerations in developing cosmetic formulations that meet consumer needs and regulatory standards. Flavors and fragrances rely on complex chemical compositions to create specific sensory experiences. Chemists use natural and synthetic compounds to mimic the aromas and tastes of various substances, enhancing the appeal of foods, beverages, perfumes, and other consumer products. Natural flavors and fragrances are derived from plant and animal sources, while synthetic ones are produced through chemical synthesis in laboratories. Both types undergo rigorous testing to ensure safety and compliance with regulations. Chemical manufacturing and waste disposal can have significant environmental impacts, including pollution of air, water, and soil. Chemists work to minimise these impacts by developing cleaner production processes, recycling waste materials, and implementing sustainable practices. Green chemistry is a field that promotes environmentally friendly approaches to chemical synthesis, production, and waste management. It focuses on reducing or eliminating hazardous substances, conserving resources, and minimising energy consumption throughout the life cycle of chemical products. Biofuels are renewable energy sources derived from organic materials, such as plant biomass, agricultural residues, and algae. Chemistry plays a crucial role in biofuel production through processes like fermentation, hydrolysis, and catalytic conversion. The chemistry contributes to the understanding and treatment of diseases by elucidating the molecular mechanisms underlying biological processes. It provides insights into the interactions between drugs and biological targets, helping to develop more effective and targeted therapies. The body's metabolism and physiology involve numerous chemical processes, such as digestion, respiration, and cellular metabolism. Chemistry studies these processes at the molecular level, providing insights into health and disease. Pharmacology is the study of how drugs interact with living organisms to produce therapeutic effects. It intersects with chemistry and drug discovery, where compounds are designed, synthesized, and tested for their pharmacological activity, efficacy, and safety. Chemists play a crucial role in addressing antibiotic resistance by developing new antibiotics, understanding resistance mechanisms, and optimizing existing therapies. They work to design molecules that target specific bacterial vulnerabilities while minimizing the risk of resistance. Chemistry informs the development of vaccines and other medical interventions by elucidating the molecular structures of pathogens, understanding immune responses, and designing antigens and adjuvants to elicit protective immunity. Chemistry plays a crucial role in space exploration and planetary science by enabling the analysis of extraterrestrial environments and materials. Chemical analyses help scientists understand the composition of planets, moons, asteroids, and comets, shedding light on their geological processes and potential habitability. Conducting chemistry experiments in space poses unique challenges due to microgravity, radiation, and limited resources. Chemists develop specialized instruments and techniques to overcome these challenges and perform experiments aboard spacecraft and planetary rovers. Chemistry often collaborates with other scientific disciplines, such as physics, biology, and engineering, to solve complex problems and address interdisciplinary research questions. This collaborative approach leads to innovative solutions and advances our understanding of the universe. In industry and manufacturing, chemistry is essential for optimizing processes to enhance efficiency, productivity, and product quality. Chemists design and develop chemical processes, materials, and technologies used in various industries, including pharmaceuticals, energy, agriculture, and consumer goods. Quality control ensures that products meet specific standards and regulatory requirements, minimizing risk to human health and the environment. Chemists implement rigorous testing and monitoring protocols to maintain product integrity and safety throughout the manufacturing process. Chemistry is a dynamic field that continuously evolves through research and innovation. Chemists develop new methods, techniques, and materials to address emerging challenges and opportunities, driving progress in science and technology. The history of chemistry spans centuries of exploration, discovery, and innovation, from ancient alchemy to modern chemical sciences. Major discoveries and breakthroughs, such as the periodic table, atomic theory, and chemical bonding, have revolutionized our understanding of matter and transformed the world. Famous chemists have made significant contributions to the field, advancing knowledge and inspiring future generations of scientists. Chemistry concepts are pervasive in everyday life. From cooking and cleaning to healthcare and technology, understanding basic chemical principles helps people make informed decisions, solve practical problems, and appreciate the world around them. Despite its importance, chemistry can be misunderstood or misrepresented in popular culture and education. Common misconceptions include viewing chemicals as inherently harmful and chemistry as a difficult or boring subject. Improving chemistry education involves making the subject more engaging, relevant, and accessible to students of all ages and backgrounds. Hands-on experiments, real-world applications, and interdisciplinary connections can enhance learning and foster curiosity and creativity. Emerging areas of research and innovation in chemistry include green chemistry, materials science, nanotechnology, and biotechnology. These fields offer exciting opportunities to address global challenges such as sustainability, energy, and healthcare through scientific exploration and discovery. Chemistry intersects with physics through the study of matter and energy. Physics helps explain the fundamental principles underlying chemical phenomena, such as atomic structure, molecular interactions, and chemical reactions. Chemistry also intersects with biology, particularly in biochemistry, where chemical processes within living organisms are studied. Understanding the chemical basis of biological systems is essential for fields like medicine, pharmacology, and biotechnology. In the field of chemistry, current challenges include developing sustainable energy sources, mitigating environmental pollution, and combating diseases through drug discovery. Opportunities lie in advancing green chemistry, nanotechnology, and materials science to address these challenges effectively and sustainably. Chemistry plays a crucial role in addressing global issues like climate change by developing renewable energy technologies, capturing and sequestering carbon dioxide, and understanding the chemistry of the atmosphere and oceans. In public health, chemistry contributes to drug development, water treatment, and disease prevention through research, education, and policy initiatives. Individuals with a background in chemistry have diverse career paths available to them, including research and development, education, healthcare, environmental science, and industry. Chemists can work in academia, government agencies, private companies, and non-profit organisations, applying their expertise to solve real-world problems and drive innovation. Chemists communicate their findings through scientific publications, conferences, and collaborations with colleagues. They use various communication tools such as journals, presentations, and reports to share their research findings and collaborate on interdisciplinary projects. Resources for learning about chemistry include textbooks, online courses, educational websites, and scientific journals. Chemistry-related organisations, such as the American Chemical Society and Royal Society of Chemistry, provide valuable resources, networking opportunities, and professional development for individuals interested in the field. Chemistry contributes to technological advancements and innovation by developing new materials, chemicals, and processes that improve our daily lives. Examples include advances in renewable energy, nanotechnology, pharmaceuticals, and electronics, which rely on chemical principles for their development and application. Chemistry appears in popular culture, literature, and art in various forms, from iconic chemical symbols like the periodic table to fictional portrayals of chemists and chemical reactions in movies and books. Artistic interpretations of chemical structures and phenomena can also be found in visual arts and design. In physical chemistry, key concepts and principles revolve around the study of the behaviour of matter and energy at the molecular and atomic levels. This includes understanding concepts such as thermodynamics, kinetics, quantum mechanics, and spectroscopy. These principles help explain how and why chemical reactions occur, how substances interact with each other, and how energy is exchanged during these processes. Computational chemistry uses computer simulations and modelling to predict and understand chemical phenomena. It involves applying quantum mechanics, molecular dynamics, and statistical methods to simulate molecular structures, reactions, and properties. Computational chemistry aids in drug discovery, materials design, and understanding complex chemical systems. Quantum chemistry is a branch of chemistry that applies quantum mechanics to describe the behaviour of atoms and molecules. It involves solving the Schrödinger equation to obtain information about the electronic structure and energy levels of molecules. Key concepts in quantum chemistry include wave functions, orbitals, and electron density. Computational methods in quantum chemistry, such as density functional theory and ab initio methods, are used to calculate molecular properties and predict chemical reactivity. Polymer chemistry is the study of the synthesis, structure, and properties of polymers, which are large molecules composed of repeating subunits called monomers. It involves designing and synthesizing new polymers with specific properties for various applications, such as plastics, adhesives, and biomedical materials. Polymer chemistry techniques such as polymerization reactions and polymer characterization methods are used to study and manipulate polymer properties for desired applications. Polymer chemistry finds extensive applications in plastics and materials science. Plastics such as polyethylene, polypropylene, and polystyrene are ubiquitous in everyday life, from packaging materials to electronic devices. Polymer chemistry enables the design and synthesis of polymers with specific properties, such as strength, flexibility, and thermal stability, to suit various applications. Additionally, polymers are used in materials science to create advanced materials with tailored properties for specific uses, such as composite materials, coatings, and membranes. Chemical kinetics is the study of reaction rates and mechanisms, focusing on how quickly chemical reactions occur and the pathways they follow. By measuring reaction rates under different conditions, chemical kinetics provides insights into the factors affecting reaction speed, such as temperature, concentration, and catalysts. This information is vital for optimizing reaction conditions in chemical processes, such as industrial production and catalysis. Chemical kinetics also plays a crucial role in understanding complex reaction networks and designing efficient reaction pathways for synthesis and manufacturing. The thermodynamics deals with the study of energy and its transformations in chemical systems. It provides fundamental principles for understanding and predicting the direction of chemical reactions based on energy changes. Thermodynamics helps quantify energy transfers during chemical processes, including heat exchange, work done, and changes in entropy and enthalpy. This knowledge is essential for designing chemical processes, optimizing reaction conditions, and predicting the stability and feasibility of chemical reactions. Thermodynamics finds applications in various fields, including chemical engineering, materials science, and environmental science, guiding the design of energy-efficient processes and sustainable technologies. As for current trends and challenges in chemistry, there is a growing emphasis on sustainability, green chemistry, and interdisciplinary research. Chemists are increasingly focused on developing environmentally friendly processes, renewable energy technologies, and materials with minimal environmental impact. Moreover, interdisciplinary collaboration between chemistry and other scientific disciplines, such as biology, physics, and materials science, is becoming more prevalent, leading to innovative solutions to complex problems. Additionally, advancements in computational chemistry, data analytics, and machine learning are revolutionizing chemical research, enabling scientists to explore new frontiers and tackle challenging scientific questions more effectively. As we conclude today's exploration of chemistry, we hope you've gained a deeper appreciation for the fundamental principles that govern matter and energy. Don't forget to subscribe to Loops and Loops for more captivating content on chemistry, chemical reactions, and the wonders of the molecular world. Let's continue to loop in new knowledge, foster our curiosity, and deepen our understanding of the chemical processes that shape our world. Until next time, keep those loops tight, keep exploring, and keep marveling at the wonders of chemistry.